In this video, we will compute a limit using the squeeze theorem. So we're given this limit, and in your head you should go through your checklist of the things to try from easiest to hardest. Easiest thing being just plug in 0, 0, but quickly see you can't do that. Makes the denominator 0. Next, you might try algebraically manipulating it, trying to simplify it. That's also not going to work here. The next thing we might do is try the two-path test, as in the previous video. And I'll tell you right now that's not going to work, but let's try it just to see what happens. So maybe the limit doesn't exist then. So we'll approach along all possible straight lines, y equals mx, and what will we get? If we plug in y equals mx, we get x times mx squared over x squared plus mx squared, which is m squared x cubed over x squared plus m squared x squared, which is 1 plus m squared times x squared. And we can cancel an x squared on the top and bottom. M squared over 1 plus m squared times x. And now, as x goes to 0, this limit is just 0 for all possible values of m. So all paths of approach give 0. As was discussed in the previous video, this doesn't really tell you anything. It might make you suspect that the limit exists and is 0, but you don't know for sure at this point. So as in the previous video, maybe you could cleverly try other paths that aren't straight lines, like y equals x squared, y equals x cubed, or even something else. But as you'll quickly see, if you try different things like this, you'll keep getting 0 over and over and over again for all possible paths. But you can keep trying paths all day, more and more different types of paths, and you'll just keep getting 0. But this will never actually prove that the limit is 0. You need to somehow use something clever and stronger. Again, as we said in the previous video, trying multiple paths can only ever tell you that the limit does not exist. It can never tell you for sure that the limit does. And I'll tell you right now, this limit does exist. So let's not just keep trying paths, let's try something more clever. As we hinted at before, we'll use the squeeze theorem. So, just a quick reminder, what does the squeeze theorem say? The squeeze theorem says that if you have two functions, g and h, where one is always smaller than the function f, and one is always bigger than the function f, and if the limit of g is the same as the limit of h as xy approaches something, in general I'll call it ab, then f has the same limit. And let's call that number capital L. Then the limit of f is also L. So So again, the squeeze theorem says this. If the function f is squeezed between two functions, one bigger and one smaller, and those two outer functions, the bigger and the smaller one, g and h, have the same limit at some point, then f is forced to have that same limit as well. So we want to use this to say that our particular f, which is this xy squared over x squared plus y squared, goes to 0 as xy goes to 0, 0. So it is our goal here to find appropriate choices for g and h that will make this work. So we need two things. We need to find g and h that satisfy this inequality. So a function that's always smaller than the one we're given, and another one that's always bigger. But not only that, we need both of the functions we pick to have the same limit, which we know from above, if it's going to exist, it's going to be 0. So we need to find two functions that go to 0, one bigger than f, one smaller than f. So at this point it becomes sort of a creative exercise to use the squeeze theorem. It's not always really super standard what you should pick. You have to have a little intuition and creativity to sort of figure it out. But let's look at the function we're given and see if we can't figure something out. So let's note one thing right now. Let's ignore the x in the numerator and just look at the rest of it. So let's notice something. Y squared over x squared plus y squared, which is the function we're given without the x. This is smaller than if we were to add x squared in the top. That's just because x squared can only be positive, it can't be negative. So if we were to add x squared on the top, it would only get bigger. But then that makes it the same as the denominator, so that's equal to 1. So in other words, this quantity y squared over x squared plus y squared is less than 1. So it's some small fraction. So what does that mean? This means that the thing we were given, which I'm going to write it a little differently, write it like this. X times y squared over x squared plus y squared. Right, this is the original thing we were given that we're trying to find the limit of. So it's x times something smaller than 1. So that means its magnitude is smaller than that of x itself. Since we start with x and multiply by some fraction that's smaller than 1, it gets smaller. So it's between 0 and x. So it looks like maybe we have our inequality right now. Maybe we can take g in the squeeze theorem to be 0 and h to be x. This thing is between 0 and x. But there's one problem with that. We don't know if x is positive or negative. So we don't know if 0 should be on the left or the right. If x were positive, then this would be fine. We could take g to be 0 and h to be x. If x were negative, you would have to go the other way then, because 0 would be bigger than x. So we would have to use g is x and h is 0. But x is a variable, so we don't know what it is. It could be either. But there's a clever way to get around that. We could also say that this same thing is between negative the absolute value of x and the absolute value of x. So this sort of gets around the fact that we don't know if x is positive or negative. If x were positive, this is just saying that x times some small fraction is in between negative x and x. If x is negative, then it's just flipping it and saying it the other way around. And now we have our g and h that we can use for the squeeze theorem. Because now this works regardless if x is positive or negative because of the absolute value bars. So now take g of xy to be minus the absolute value of x, and h to be the absolute value of x. So again, since this fraction here is smaller than 1, multiplying x by it shrinks it closer to 0, so it's definitely going to be in this range. So to summarize what we've just said here, let's say here's 0, here's x, here's minus x. We've multiplied x by something smaller than 1, so it goes somewhere here or something. Or if x were negative, it would just be over there. So now just to finish it up, let's notice that the limit as x and y both go to 0 of both minus absolute value of x and absolute value of x are both 0. So now here's our conclusion. So by Squeeze theorem, the limit as xy goes to 0, 0 of our original thing, because of the inequalities that we've come up with, is also 0.